This program is brought to you by Stanford University. Please visit us at stanford.edu.
What about the complexity of the black hole if it's going to model completely this collision?
What about the complexity of it?
Yeah, in other words, it's not a stable black hole. It must be something that's changing shape and things like that. Right?
Yeah. That's right. Here's the picture. You have a fifth dimension, and think of the fifth dimension as existing between a floor and a ceiling. Ceiling, floor. There's a gravitational field that pulls everything down to the floor. There are particles or strings or whatever they are which can live in this five-dimensional world. Let's think of them as little strings. And they tend to fall to the bottom here. When they fall to the bottom, they're hadrons. They're protons, neutrons, mesons, and so forth. If they get stuck up at the top, and they can stick to the ceiling, they can stick to the ceiling. If they're stuck up at the top, they are gravitons, photons, more elementary particles, not hadrons. Hadrons are big, fat, composite objects. When you collide two hadrons, that's like colliding two particles that are on the floor. They collide, they make a big splash of energy, and the big splash of energy is apparently nicely described, well described, by saying that a black hole forms. A black hole is just a big puddle of energy. A big puddle of energy, a lump. A lump with an edge. The edge is the horizon, and like all black holes, they have temperature, they have entropy, they have all the thermodynamic properties of black holes. And this object is a kind of black hole that's sitting down on the floor. It's not the kind of black holes, four-dimensional black holes that we think of as astronomical black holes, or the kind of black holes that we would make by scattering particles at enormous energies above the Planck scale. Those kind of black holes also have horizons. They're very similar, except they are droplets hanging from the ceiling. Actually, they hang this way. Hanging from the ceiling, attached to the ceiling, and they are stuck to the ceiling. The ceiling is a sticky ceiling. But otherwise, they're the same kind of thing. They're the same kind of thing in 5 dimensions. They correspond to black holes, they correspond to horizons, and they correspond to all the things that Stephen Hawking and others have studied over the years. Now, if an enormously high energy collision happens, an enormous lump of energy, remember what happens to particles which are very high energy. They get collapsed like thin pancakes by lorentz contraction. So what happens is two pancakes. They're moving in this direction, in this direction. They're thin, they're like pancakes. So I don't know how to draw it exactly. Whatever they are, they're thin in this direction, and they come in and they collide. They collide with an enormous amount of energy, and they make a great big puddle of energy like that. But that puddle of energy is more or less like a lump of viscous fluid, and not so viscous, rather unviscous, a lump of fluid that's been deposited in this gravitational field. And the gravitational field pulls it down and spreads it out. And spreads it out until it comes to some equilibrium, like a puddle on the ground. And it would stay that way except for one thing. And the one thing is Hawking radiation. Hawking radiation starts causing radiation to come out off this thing. And what is that radiation? That radiation is the ordinary particles that we see, the protons, neutrons, mesons, and so forth, that we see coming out of this thing. Remember when he showed us some of the pictures of the events there was this 7,000 particles coming out of a little dot here. Those 7,000 particles are, in this picture, they're essentially the Hawking radiation that's boiled off the outer parts of this black hole here. As I said, whether you should really think of it as a fifth dimension and real honest-to-goodness black hole sitting on the floor of the fifth dimension here, or whether you should just think of it as a mathematical analogy, at this point I would say is up to you. I think in time we will understand better the connection between these ideas and real gravity. My own guess is they will be connected in a deep way, and that we will learn to understand this picture as part of a bigger thing, part of, will it be string theory, will it be quantum gravity, will it be something that we haven't seen yet? But yeah, I think the fifth dimension is quite real. What does it mean to be real? It means it fits together with the other dimensions in a mathematical structure that, I don't know, that makes the laws of physics look simple. Dividing this into real space and a fictitious space and treating the fictitious space completely different seems to make the equations more complicated than if you think of, if you really literally think of this as a fifth dimension. But this five-dimensional structure here really is nothing but quantum chromodynamics. QCD, the theory of quarks and gluons. So, as I say, at the moment, it's kind of up to you whether you want to think of it as having any reality or whether you just want to think of it as a mathematical analogy that allows you to do difficult problems easily.
So that fifth dimension is a spatial dimension?
Yeah.
Space-like?
Yeah.
That line that you got drawn there, so that's actually extending out into the spatial dimension?
Say it again. Which line? I've got many lines.
Bottom.
This one?
Yeah.
That's in the spatial dimension. Yeah, these are space dimensions.
So
everything's space here.
That would correspond to a horizon located in that fifth.
Well, this would correspond to a horizon. This, yeah.
What you're saying right now, though, is experimentally, there's really not, what they've observed is not, could also be explained just sort of the ideal, you've got a big fireball of random, particles being created by energy, thermal energy.
Yeah. Well, yes. The details of it, the devil is in the details. This prediction about the viscosity was a stunner. Nobody expected that. So that was purely the only explanation of that, or the only quantitative explanation of it, comes from the parallel with black holes. That was a stunner. That was not expected. There are other interesting things, other interesting kind of experiments, the way particles move through this plasma. The details of it may be better described by thinking of it as a black hole than thinking of it as, thinking of it in terms of quantum chromodynamics and doing quantum chromodynamics correctly and calculating it honestly, if we knew how to do that, should give us the same answers. It's not that this theory is replacing an older theory. It's believed to be a mathematically equivalent description, but one that's useful in contexts where we simply can't calculate quantum chromodynamics. In fact, we've never been able to calculate quantum chromodynamics very effectively, except in some very, very special situations.
QCD doesn't have gravity or doesn't have horizons in it.
No, that's right.
So there's some new thing there.
Well, in its five-dimensional incarnation, it does have gravity and it does have horizons. In its four-dimensional version, this is just a hot fireball of quarks and gluons without gravity.
That's what I'm asking, but there is the viscosity.
Yeah.
There's something that maybe.
Right. The viscosity can always be described in principle by understanding hot quarks and gluons. But when I say in principle, nobody has learned how to do that. Quantum field theory is a difficult subject. Nobody knows how to calculate those sorts of things. The equivalence with gravity, of course, is also hard, but some things are easy. Some things are easy, and as it happens, calculating the viscosity of a horizon is easy. Yeah.
Are we going to be able to figure out why they collide the beams instead of running the beam into a still?
What? Say it again?
Are we going to be able to understand why they collide the beams instead of running the beams into a still target?
Oh, yeah, no, that's easy. That's easy.
Is that tonight's lecture?
What's that?
Is that in tonight's lecture?
Well, I didn't include it in tonight's lecture. It very well could have been, but let me tell you the answer. If, all right, there's something called center of mass energy, which is the energy of the system when it's viewed from the center of mass frame. In other words, when the two particles are colliding with equal and opposite momentum. The center of mass energy is called E, naturally. Okay? And that's equal, roughly speaking, in units in which C is equal to 1. It's just equal, these are very relativistic particles. Relativistic particles have an energy which is equal to their momentum. And so it's just equal to twice the momentum of these particles. In fact, and that can be very large. On the other hand, if you slam the fast particle into a standing still particle, and you ask, what's the center of mass energy of that? In other words, what would be the energy if you went to the center of mass of this? The energy would be much smaller. Much, much smaller. It wouldn't be twice the momentum. It would be something like the square root of the mass of this particle times the momentum of the fast particle here. That's much, much smaller. This is much smaller than this if the momentum is large. So the point is that you lose an enormous amount of effective energy by letting this particle stand still. If you can accelerate it to the same speed that the other one is moving, that doesn't give you twice the energy in effect. It gives you the square of the energy, basically. So it's a much more energetic collision to have them collide head-on. We will be able to do that. We'll be in a position to do this in detail, but not now. But that's the reason, energy. Yeah.
Is there a reason why a cyclotron has to be so large? Is that a fundamental reason, or is it just it's happening magnetically?
Well, you know, electric and magnetic fields can only be so big before they can't be supported by steel and concrete and the other things that hold the accelerator together. You can only create magnetic fields which are, 10 Tesla or something like that, and it's the magnetic fields that are accelerating the particles. And so you can't accelerate a particle. Simply, it's not a matter of, in principle, it's a matter of strength of materials, all sorts of engineering things, and ability to create huge magnetic fields that limit the ability to accelerate particles over short distances of space. You simply can't create big enough fields to accelerate a particle to a relativistic energy, a proton to a highly relativistic energy over a meter. The more you want to accelerate it, the more room you need, because all the acceleration is as it moves along, you give it a push, you give it a push, you give it a push, you give it a push. And so you got to give it a lot of pushes. And that's all it is. I mean, basically the energy of the accelerator is proportional to its length, because it just accelerates with a more or less uniform energy per meter.
So they can't make it where it circulates a few times, but the cyclotron to be smaller?
Oh, well, then I think you would simply run into the, I mean, it's not a cyclotron. I think you simply can't create big enough magnetic fields lasting long enough. No, there's another very important point. The other very important point has to do with energy loss. When you accelerate a particle, a charged particle, first of all, you can only accelerate charged particles. You can't accelerate neutral particles. Now, charged particles, when they move in circles, accelerate. And the smaller the circle for a given velocity, the bigger the acceleration. So a particle moving in a tight little circle is highly accelerated. Acceleration means radiation, and radiation means energy loss. So there's a very, very important technological point here that if the circle is too small, it will simply lose energy at a rate which is as big as you're dumping the energy in. You're limited in the size of the accelerator by not wanting it to lose energy by radiation too fast. A straight accelerator doesn't, a particle moving in a straight line with uniform velocity doesn't accelerate and doesn't radiate. Right? So if you give it a push, a push, a push, a push, well, there's a little bit of acceleration, all right, which causes it to radiate, but making it turn around in a circle really causes big problems. Those problems can sometimes be advantages. For example, up at SLAC, they run electrons in circles and they take off the synchrotron radiation, the radiation that comes off, and they use it for other purposes. But if your point is to get a lot of energy into your charged particles, you want to accelerate them in as straight a line as possible, because in that way you eliminate the tendency of the particles to radiate away their energy.
Is there it seems to me that the straight line in SLAC is electrons, and these circular ones are hadrons.
Yeah.
Is there a reason?
Yeah. Electrons are much lighter than protons. So to get a given amount of, it's energy that's important. You want to dump energy into a small volume and see what comes out, okay? Now, electrons are very much lighter than protons. So in principle, you've got to get them up to a larger velocity for the same energy. You've got to get them up to a larger velocity, and in getting them up to a larger velocity, that also means for a given circle, a larger acceleration. So if you were to accelerate electrons in the Hadron Collider, they would be subject, and try to get them up to the same energy, they would have a much larger acceleration and a much larger energy loss. So again, it's energy loss. The light particle needs to go faster to have the same energy. Faster means more acceleration when it goes in a circle. Acceleration means...
yeah, but what about the other way? Why not hadrons in the linear accelerator?
Well, one... you could do hadrons in the linear accelerator. Why not hadrons in the linear accelerator? You get to accelerate it many, many times as it goes around in the circle. Going around in the circle and accelerating it is equivalent to having an enormously big accelerator. You get to push it and push it and push it and push it and push it. So you could do it in the linear accelerator, but you have to make the linear accelerator very, very much bigger. You want a good long length to do it in, but you don't want too much radiation. For hadrons, the compromise is to have a big circle and to keep accelerating along its route until it's limited by the radiation. But it'll be limited by the radiation at the same velocity that the electrons would be limited by their, all right? Same velocity, but that means much more energy for the protons. Okay. Let's get back to the special theory of relativity. And just for fun, let's do one puzzle. All problems in special relativity, all puzzles in special relativity are usually the same. They have to do with one basic flawed concept that we carry around as evolutionary baggage and confuses us every time we have some relativity problem. The thing to do is to draw a good diagram and to remember in detail what that diagram is telling us. Here's the puzzle. It's a famous puzzle. It's usually phrased in terms of a limousine trying to get into a garage. So you have a garage a certain size, let's say 12 feet in length, 13 feet in length. I don't know how long my garage is, probably longer than that. But just big enough that an ordinary car can fit into it. And a stretch limousine wants to get into it. I don't know how, I'm not, it looks like it's going this way. And the stretch limousine is 20 feet long. Wants to get into the garage. So the driver says, okay, I know the special theory of relativity. I'll speed up my car, and whoever's watching from the rest frame will watch this. Somebody watching from the rest frame will watch this, and according to his calculations, my car will be Lorentz contracted in the frame of reference of the garage. It'll be Lorentz contracted, and if I can Lorentz contract it enough by making it move fast enough, I can get it into the garage. Getting it into the garage means the front end and the back end are both within the garage simultaneously. Okay. On the other hand, the other view of it is that the car is standing still and the garage is moving toward the car. And so from a frame of reference in which the car is standing still, the garage looks Lorentz contracted and therefore is much smaller than the size of the limo, and it's quite clear that the limo can't get into the garage. So we have a puzzle. We have a paradox. Can the limousine get in, or can't the limousine get into the garage? Now, as I said, what it means for the limousine to be in the garage is that the front end and the back end are simultaneously inside the garage. And the nasty concept that we've inherited and we have a difficult time getting rid of is the concept of simultaneity, what it means for the two ends of the car to be simultaneously inside the garage. That's the rub, that simultaneity is not the same in all reference frames. So the thing to do to understand this particular problem, well, first of all, we ought to open the door to the garage to let the car in. So I'm going to open the door. But just for safety's sake, I'm also going to open the back door. And we'll simply ask, is the car ever simultaneously, all of it, inside the garage? We won't worry about what happens. If it gets in the garage, we won't worry too much about what happens when it's decelerated by the back wall of the garage. And the way to avoid that is we will simply open up the back door. I don't want to kill a driver. I do wish I had a better piece of chalk, though. Okay. So how do we analyze this? As always, the first thing to do is to draw yourself a picture. Ah, that's a good one. Draw yourself a picture and get everything laid out on the picture. Vertical axis is time. This is all a problem that takes place in one dimension of space. So we don't have to worry very much about y and z. Pretty much x is all we have to worry about. As the first thing we draw into this diagram is the light cone, the trajectory of light rays. This just orients us. It orients us and reminds us what very, very fast means, the speed of light. All right, so we draw in light-like trajectories like this, okay? And then we begin to, then the next thing is to put in our two observers. One observer is the observer at rest, and his coordinates x and t just look like what's drawn there. The second observer is moving relative to the first with a velocity, and so his axis looks like this. This could be called t prime. Let's put it at a little bit bigger angle. The bigger the angle, the faster he's moving, and I want to exaggerate the motion. So let's put him way out here, moving with something like half the speed of light or something like that. And we also have to remember that the x-axis, the new x-axis, the x prime axis, is tilted relative to the x-axis, meaning that what the new observer calls simultaneous is different than what the old observer calls simultaneous. The old observer calls everything on the horizontal axis simultaneous, meaning to say that it happens at the same time. The new observer, the moving observer, calls everything along now, it wasn't very well drawn. One more try. I was told when you draw pictures like this and you want to make straight lines, take your eye off the chalk and only look at the end point. But it never works. Look at the end point. Okay. It just doesn't help. Yeah, it's bent over here too much. No, it's not acceleration. No, no, it's not. This is not a moving thing. This is. Yeah. Okay. Yeah, they are. They are. Yes, they are equal. In coordinates in which the speed of light is 1. You don't want to try to draw this in the coordinates in which the speed of light is 186,000 miles per second, because then this is practically horizontal, and you won't be able to see anything. All right, so in coordinates in which the speed of light is 1, the picture looks like this. Now let's draw in the garage. All right? First of all, there is, well, I don't know what they're called. Let's call it the front end. This is the front end of the garage and the back end of the garage. All right, the front end of the garage stands still in our frame of reference, and that means it looks like a vertical line. The same is true of the back end of the garage. It's also a vertical, or this end here. It's also a vertical line, and it looks like this. Whoops. So the region in here, between the two red lines, let's just dot it in. Maybe I shouldn't. Let's leave it white. The region between the two red lines is the interior of the garage. Now what about the limousine? The limousine is moving, and it's moving with velocity of the other frame of reference. The other frame of reference is the frame of reference of the limousine. Here's the back end of the limousine. The back end of the limousine over here moves, and at this point, let's draw it in green. The back end of the limousine is here. The front end of the limousine is over here. I won't draw it in yet. Okay, I will draw in the front end of the limousine. The front end of the limousine, I'm going to put, let's see, about over here. There's the front end of the limousine moving with the same speed, of course, as the back end. Here it is. Now, I've opened the back end here, the back door, so the limousine goes right through. It doesn't smash into the back wall. It just goes through. And our question is there any instant of time at which the entire limousine, in other words, the distance from the back green to the front green, or from the rear end of the car to the front, the portion of the limousine between the rear end and the front end, is there any time at which it's all together simultaneously inside the red? Now we have to decide what we mean by simultaneously. If we mean simultaneously from the point of view of the stationary observer, that's asking the question, is there any horizontal line that you can draw here in which both the back end and the front end will both appear inside the garage? And yes, there are. Here the back end goes in over here. The front end is still inside. It's right over here, the front end is, here's where the front end went into the garage. The front end crossed the beginning of the garage over here, and the front end went out the rear door over here. The back end went into the garage over here and comes out over here. Okay? So, here's a time right over here when the back end is just getting in and the front end has not yet gone outside the garage. So yes, there is an instant of time when the entire car is inside the garage. But that's from the perspective of the stationary observer. Okay. What about the moving observer? For the moving observer, lines like this are simultaneous. If I were to take this point and draw the appropriate line, it would look like that. From the moving observer's point of view, this point and that point are simultaneous. Notice that this point and this point are not both inside the garage. By the time the back end gets in, the front end is out. So from the point of view of the moving observer, no, the whole car never was inside the garage. There's no paradox, there's no contradiction. The contradiction, or the apparent paradox, is simply due to not distinguishing what we mean by simultaneous in the two frames of reference. They're the different, yeah.
The two green lines and the segment of the x-axis between the two green lines and the line that represents the vehicle being in the garage, yeah, that forms a parallelogram, right?
You mean with this?
Yes.
Yeah, sure.
So no matter how fast or how slow you go, that black line is the same length as the vehicle alone.
Oh yeah. Well, that line has a length which is the Lorentz contracted length of the limousine. This is the Lorentz contracted length of the limousine. Okay? It's the Lorentz contracted length because it's the length of the limousine as seen from the stationary reference frame. Okay? If I were to calculate the proper distance from here to here, that would represent the length of the limousine in the limousine's reference frame. Yeah. Good. All right, that's a little puzzle that's sort of illustrative of a large number of puzzles in relativity theory, and usually the answer is to remind yourself that simultaneity is a relative concept. And almost always when you analyze the experiment for these kind of puzzles, there's a hidden use of the word simultaneous, and that's where the paradox comes in. Okay, now we want to get back to Lorentz transformations, to the mathematics of Lorentz transformations. And we want to move on and understand the laws of physics as they are described in relativity theory. The same laws that are, for example, Newton's laws of force, Newton's laws of motion, and so forth. What happens to them when we move on to relativity? And we need some mathematics. Most of the mathematics is notation, not much more than notation. First of all, we have 4 coordinates, x, y, and z, and the 4th coordinate, t. It's a convenient notation to lump them all together. T, x, y, and z. In fact, I usually put t at the end. And call them all by the name x, x1, x2, x3, and x0. Why 0 instead of 4? I don't know. That's a standard notation. Maybe I should have put the x0 at the beginning, but throughout my notes I seem to have put the x0 at the end of the line. x0, x1, x2, x3, those correspond to x, y, z, and t. So the odd man out here is x0. It's the one that is time. The other 3 are spatial axes. Okay. Altogether, we also lump them all together and call them x mu. Mu, the Greek letter mu, coming from the rear end of the alphabet, represents the indices 1, 2, 3, and 4. Mu can go from, not 1, 2, 3, and 4, 1, 2, 3, and 0. X. Yeah, we're setting c equal to 1. Yeah, we are setting c equal to 1. And when it's interesting to do so, I'll put the c's back. Only when it's interesting to do so. For example, when we take non-relativistic limits of situations and we want to see how things behave for slowly moving objects in a more conventional situation, then it's convenient to put the c's back in to see how we approach the ordinary physics.
And that would be CT or x divided?
Yeah, that would be CT, right. that would be CT. Yeah, exactly. Okay, exactly. Now, there's another symbol, which is x with a lower mu. Mu in this expression goes upstairs. These are incidentally called, let's see, these are called contravariant indices. I always forget which one is which. When they're upstairs, they're called. Co is low. Co is low? And contra is high. Okay. Physicists call it upstairs and downstairs. We never use that language. We talk about upstairs and downstairs. I will. Okay. This again. Which is it? Co is low. Co is low. Okay. So these are the covariant components. These are components of an object, of a vector. We'll see. But there are two ways to describe. This is just two different descriptions of the same thing. And the difference in the description is that in the covariant components of the same vector, you write them as minus x, minus y, minus z, and t. In other words, you take the same object and you just consider the space components made negative. If I give you a point, x, y, z, t, and tell you those are the positions of a certain point, and then ask you, what are the covariant indices of that point? What are the covariant description of that point instead of the contravariant? You just multiply the space components by -1. That's its definition. You simply change the sign of the first three components. Why do you do that? You do this only for a neat notation, and I'll show you what the neat notation is.
Should these be subscripts in the middle?
These are subscript. This is subscript. Oh, it's no. Okay, then we can write that this is equal. This is x1. This is equal to x1, x2, x3, x0. Okay. So x1 with a lower index is minus the x1 with the upper index. There's nothing fancy going on here. You just take the first three entries and change their sign. And that gives you a new object, which is called x sub mu. Right? So for example, if I pick the point x equals 3, y equals 2, z equals 4, and t equals 10, then the standard expression here would just be 3, 2, 4, 10. That would be x mu. X mu would equal 3, 2, 4, 10. But this would be -3, -2, -4, and 10. It's not a different point. It's the same point, but it's just a different notation for the same point. It's the same point, just a different notation for it. Just remember, when you see an object with covariant indices like this, remember, if you want to know exactly where it is in space-time, change the sign of these coordinates here. Why do you do this? Well, I'll tell you, it makes a nice notation. It makes a notation which systematically makes elegant and pretty equations and helps you keep track of various minus signs that occur in relativity. Okay, let's consider the following object. Summation over mu. Now, summation over mu means you sum over 1, 2, 3, and 0 of x mu, x mu. What is this object? All right. Summation over mu means x1, x1. But what is that? What is x1, x1? x1 with a lower index is just the same as x1 with the upper index, except you change the sign. So this is minus x1 squared, which is just minus x squared. What about x2, x2. x2, x2, this is, x2 is y. Remember that x2 is y. Okay? So in the lower index representation, we change the sign, and this becomes minus y squared. And then for z, it's the same thing, minus z squared, but then plus t squared. Why plus t squared? Because the lower index and the upper index correspond to exactly the same sign for the time component. Okay. So this just reads x1, x1, with a lower index and an upper index, but that's minus x squared, plus x2 lower, x2 upper, this isn't squared, it's x2 upper, that's minus y squared. Next one is minus z squared, and then plus t squared. But that's exactly the opposite, that's exactly the object that we called the proper distance from the origin, or the proper time, from the origin to the point x, y, z, t. Right. So we now have a notation, a notational trick. So far you don't see what the trick is, but you'll find out that the trick is quite useful. That we can write the proper distance from the origin to a point in just the form summation over mu, x mu, x mu, with one index upper and one index lower. Now, over and over and over again in relativity theory, you'll be doing sums like this, where you sum over the first direction, the second direction, the third direction, the fourth direction, with the first three of them having the opposite sign from the last one. That happens over and over again. In fact, it happens over and over so many times that Einstein got sick of writing the summation sign here, and he just left it out. He said, rule, whenever you see an expression like this with an upper index and a lower index, and the upper index and the lower index are the same, it means sum over the indices. It's called the Einstein summation convention. It was probably not Einstein's most brilliant accomplishment, but it was pretty damn smart. So x mu, this kind of expression where an index will be repeated once lower and once upper, and only if it's once upper and once lower, then you remember to sum over the index. And what do you get? You get the proper distance or the proper time from the origin to the point x, y, z, t. So this is a neat notation. What is it for? It's a notation for the combination t squared minus x squared minus y squared minus z squared. That's all it is. Okay. And tau is the standard symbol for proper time. Sometimes called S. But yes, tau is a standard, is a standard symbol for proper time. Okay. All right, we'll use that over and over. It gets tiresome to write down x squared, t squared minus x squared minus y squared minus z squared. And so this is the notation that we'll use. That's one piece of mathematical notation. I won't call it mathematics. It's just notation that is very, very convenient when studying relativity. In fact, it would be very difficult to write the equations of relativity without this notational device. Okay, next, let's talk about transformation laws in general. In fact, let's talk about not Lorentz transformations. Lorentz transformations are things which mix time and space together. For example, if you consider two observers which are moving relative to each other along the x-axis, then we have Lorentz transformations which mix x and t, leave y and z alone. Those are Lorentz transformations. And the principle of relativity is a principle of symmetry that says the equations of our theory should be symmetric, should not change when we make a Lorentz transformation. Well, there are other symmetries that are more familiar. the simplest of which is just rotation of coordinates in space, ordinary spatial coordinate rotations. In fact, if we combine the two together, Lorentz transformations and spatial rotations, we get a large number of transformations which represents basically the entire set of symmetries of relativistic physics, almost the entire set. But here's the point. Let's draw in one more axis. Here's x, here's t, and let's draw in y. Z is somewhere in the fourth dimension. We can't see it, but it's also there. Now, I've taught you how to do Lorentz transformations along the x-axis. In other words, I've taught you how to compare the coordinates of a moving observer who's moving along the x-axis with the coordinates of the stationary observer. Right? I don't think it would be too hard. Oh, and remember what it does. It mixes x and t together, but leaves y alone. Right? It leaves y alone. It does not transform the coordinate perpendicular to the motion, to the relative motion. So everybody agrees about y, but they disagree about t and x, but nevertheless they transform into each other under Lorentz transformations. Now, I think you could probably figure out if instead of thinking of two observers moving relative to each other along the x-axis, suppose we had the second observer moving along the y-axis. I think you could probably figure out how to do the transformations. Instead of writing things like x prime is equal to x minus vt over square root of 1 minus v squared, t prime equals t minus vx over square root of 1 minus v squared, and y prime equals y, and also z prime equals z, all you would really have to do is interchange x and y and write that y prime is equal to y minus vt, t prime is t minus vy, but x prime is equal to x. That wouldn't be very hard. You just realize that what you originally called the x-axis has now become the y-axis, and simply make that replacement. But supposing you wanted to do a Lorentz transformation, in other words, you wanted to consider an observer who was moving along some funny axis, neither x nor y, but along some funny angle. Then the thing to do would be, before you make the Lorentz transformation, do a rotation of coordinates in space. Find a new coordinate x prime and a new coordinate y prime, which are just rotated in space, and then do your Lorentz transformation along the new primed axes. Right? By compounding together rotations of space with Lorentz transformations along one axis, you can construct all of the possible frames of reference moving relative to each other with uniform velocity. Right? If they're moving along not along one of the original axes, all you do is rotate coordinates rotate spatial coordinates until you have your axis of motion aligned with one of the new axes, and then do the Lorentz transformation along there. Okay. So the other thing then that we have to know is how to transform coordinates under rotations of space. Now this is something that has nothing to do with Einstein. It goes back probably to Euclid. I don't know who was the first one who figured out how to rotate coordinates. I don't know if Euclid used coordinates of vectors, and so I don't think he did. But who does that go back to? Descartes? I'm not sure. Descartes? Probably Descartes. Yeah, so, but in any case, it goes way, way back past Einstein, just rotations of coordinates. Every rotation in space has an axis. Right? We can pick our axis. Let's pick the z-axis to rotate around. If we pick the z-axis to rotate around, then only x and y transform. All right? Z stays the same. So we're rotating about the z-axis I don't know where z is. Z is vertical, and we're rotating about that axis, and so x and y get mixed up with each other. Let's just write down. I'm not going to prove. It takes a little bit of trigonometry to figure out what the transformations are. Let's draw the xy plane this way. Here's x, here's y. Here's x prime, here's y prime. The angle of rotation is theta. And here's some vector with coordinates xy. The question is, and coordinates xy means that if you drop it perpendicular to the x-axis, it'll intersect at point x. And if you drop it perpendicular to the y-axis, it will give you y. Now, you want the primed coordinates. The primed coordinates after rotation, you do the same thing. You drop a perpendicular to the x prime axis, you drop a perpendicular to the y prime axis, and you look at the coordinates in the x prime and y prime axis. Right. So that's the geometry. That's the geometry of the coordinate transformation from x and y to x prime and y prime. It's just a matter of dropping perpendiculars to the appropriate axes. All right, I'm going to give you the formula for x prime and y prime in terms of x and y. It depends on the angle theta, and you can check this. It's a little bit of trigonometry, elementary trigonometry. X prime is equal to x cosine theta plus y sine of theta, and y prime is equal to minus x sine theta plus y cosine theta. You can check that, for example, when theta is 0 degrees. What does it say when theta is 0 degrees? Sine of theta is 0, cosine of theta is 1. So it says x prime is equal to x, and it says y prime is equal to y. That's good. A rotation by 0 degrees is no rotation at all. Now try a rotation by 90 degrees, and you'll see that it also works. And that's the general rotation of coordinates. Now, this transformation, there's something which is left invariant by this transformation. It's the distance to the point xy. By left invariant, I mean that the distance, the square of the distance to the point xy, what is that? The square of the distance is x squared plus y squared. If you move the point out of the plane, you might also add in z squared. Oh, let's say it in z. Z prime is equal to z. You're rotating about the z-axis, and so nothing happens to z. All right. What this transformation leaves invariant is x squared plus y squared plus z squared. Let's start with x squared plus y squared. Let's forget z for the moment. That means that after you've made the transformation, x squared plus y squared is the same thing as x prime squared plus y prime squared. Well, geometrically the reason is because it doesn't matter whether you calculate the distance by referring to the original coordinates or the rotated coordinates. The distance must be the same. Distance is what you measure with a tape measure, and the tape measure doesn't know where your coordinates are, so the answer has to be the same. X squared plus y squared must be equal to x prime squared plus y prime squared, but you can check that. You can check that. For example, x prime squared is, let me just call cosine theta c and sine theta s, so I don't have to write so much. X prime squared. What's x prime squared? That's x squared c squared plus y squared s squared plus twice xy cs. X squared c squared plus y squared s squared plus twice the cross term. That's x prime squared. What about y prime squared? That's y prime squared is x squared s squared from here plus y squared c squared from the second term, and then minus, because there's a minus sign here, minus 2xy cs. Now add them together. All right? On the left-hand side, you just get x prime squared plus y prime squared. But on the right-hand side, you get x squared times cosine squared plus sine squared. Cosine squared plus sine squared is 1, right? So that's just x squared. Y squared, you also have s squared plus c squared, so that's just y squared. And the cross term here just cancels. 2xy cs and minus 2xy cs. This goes away. All right, so we're only proving what's obvious anyway, that the expression for the distance doesn't depend exactly on how you orient the axes. It's always just x squared plus y squared. If we added in z prime equals z, since z is equal to the same as z prime, we could also say that the distance in 3 dimensions is unchanged. Z is the same as z prime, so there's nothing new there. The rotations, mathematically, are transformations on the components which preserve the length, which keep the length unchanged. That's the mathematical definition of the rotations. All right. Now, there's another way to write such a transformation. I wonder, people seem to be walking in. They seem to be a little bit confused. Is this 200 or is this 201? No, it's 201. Okay. Yeah. Yeah. Okay, so that's the idea of rotations. If you combine the rotations with Lorentz transformations, in other words, after having made the transformation to x prime and y prime, and also t prime is equal to t, if you like, if you want to think about the full 4 dimensions, then you can go and do a new Lorentz transformation along the x prime t prime axis, and in that way build an observer who is moving along the new x prime axis rather than the old x-axis. Okay. So combining rotations and Lorentz transformations basically gives you a wide class of different transformations which correspond to the rotations of all kinds and Lorentz transformations along all the possible axes that you could do them along. All right, now more notation. More notation. Notation is boring, but once you get it, you've got it, and it makes equations much easier, simpler, and easy to manipulate. Everybody here know a little bit of linear algebra? That's the wrong question. Does anybody here not know a little bit of linear algebra? Everybody knows linear algebra. Good. We don't need to, okay, good. That's excellent. All right, now there are 2 ways that we could write these equations like this. Let's just take this one here. We could write it in a matrix form. X prime y prime is equal to some matrix times xy. The matrix would in fact just be cosine theta, sine theta, minus sine theta, cosine theta. We could also write it in another form. We could write x, and we could also put here z prime, z, and then the matrix would be a 3 by 3 matrix, 0, 0, 1. The matrix would then act among the xy components here to mix them up, leaving z out of the picture altogether, and then it would act on z to give z prime, which would just be z equals z prime. So every such transformation has a matrix associated with it. And there's another way to write this. We could also write this in another form, x I prime. Now I is only going from 1 to 3. So far I haven't mixed in time. X prime I could be 1, 2, or 3, representing x, y, or z, is equal to to mij xj, where mij just represent the components of the matrix. This is the same expression, multiplying and summing over j. As always, when we see repeated index, we sum over j. In this case, since it's only got to do with space and no time, no different. Well, I'm not going to worry about upstairs and downstairs indices. It's only when time comes into it that we worry about that. This is a way of writing a vector is equal to a matrix times a vector, and we can write it this way here. Both exactly the same expression. Okay, any question about that? Because if you know this, then we can move on to Lorentz transformations. Lorentz transformations also have a similar form. They're also matrices multiplied by components. So let's work that out in detail. Let's work out the matrix associated. This is the matrix associated with a certain rotation. This isn't the most general rotation. This is the most general rotation about the z-axis. We could rotate about some other axis, and it gets more complicated. But this is typical of a rotation matrix. Good. Let's write a Lorentz transformation. X prime is equal to x minus vt over square root of 1 minus v squared. Y prime is equal to y. Z prime is equal to z. And t prime is equal to t minus vx divided by square root of 1 minus v squared. This is just our good old Lorentz transformation, except with y and z doing nothing, staying the same. Okay. We can also write this in terms of a 4 by 4 matrix. The 4 by 4 matrix equation. Here's our matrix. Okay, x, let's label the entries. X, y, z, t, or x1, x2, x3, x0. X, y, z, t. Let's see what our entries are. The coefficient in x prime, the coefficient multiplying x is 1 over square root of 1 minus v squared. The coefficient multiplying y is 0, 0, and minus v over square root of 1 minus v squared. Let's see, 0, 1, 0, 0. 0, 0, 1, 0, and minus v over square root of 1 minus v squared, 0, 0, v over square root of 1 minus v squared. Okay, let's see what this does. I maintain that if I take the column vector x prime, y prime, z prime, t prime, and I set it equal to this matrix times the column x, y, z, t, that really is a Lorentz transformation. Let's see. What does it say? It says that x prime is equal to, let's forget this. It says that x prime is equal, do I have it wrong? No, I have it. Yeah, the fourth one here is 1. Okay. Yeah. All right, so this says that x prime is equal to x divided by square root of 1 minus v squared minus vt over square root of 1 minus v squared, with nothing mixing in from y and z. That's correct. It also says that y prime is equal to y, z prime is equal to z, and t prime is minus v over square root of 1 minus v squared times x plus 1 over square root of 1 minus v squared t. That's the last equation here. So once again, a Lorentz transformation can be written as a matrix multiplying the column x, y, z, t. A rotation can be written as a matrix multiplying the column x, y, z, t. We don't usually think of the rotations as having to do anything with t, but we just think of a rotation as a spatial rotation, but that just means that t prime is equal to t when we do a rotation. So we have 4 by 4 matrices which correspond to rotations. We can call them R. And we have 4 by 4 matrices which correspond to Lorentz transformations. We can call them L. What if we want to do a transformation, a Lorentz transformation along some other axis? Right? What we do is we first use the rotation matrix to rotate axes, and then we use the Lorentz transformation matrix to boost or to give us some velocity along the new x prime axis. In other words, what it comes down to is you multiply rotation matrices by Lorentz matrices. You first rotate, and then you Lorentz transform. You multiply the matrices together to find what the action would be for a Lorentz transformation along some other angle. Let me work out one useful application of matrix multiplication, not mixing rotations into the game now. We're not going to do much with rotations of space and Lorentz transformations simultaneously. It's enough to know that our laws of physics are invariant under rotations and Lorentz transformations along one single axis. Because if they're invariant under rotations and Lorentz transformations along an axis, then they will be invariant under Lorentz transformation along any axis. So symmetry under rotation, well, that's easy. We all know how to think about that. It's symmetry under Lorentz transformations that we're interested in. What I want to work out using matrix multiplication is the compounding of velocities. If I am moving relative to you with velocity v, and there's a third observer who is moving relative to me with velocity u, okay? V, that's me relative to you. U, that's him relative to me. Got that? V relative, wow. V, me relative to you, u, him relative to me. Is that clear? I think you got it. All right. Then what's the transformation between him and you? Okay. What's the velocity that you will see him move with relative to you? Get me out of the picture. Eliminate me. Okay. That velocity we'll call w, but the trick is to find w in terms of v and u. Now, in old-fashioned pre-relativistic physics, the answer was his velocity is v plus u. I'm moving with velocity v. He's moving relative to me with velocity u. The natural expectation in ordinary Newtonian physics would be that him relative to u is velocity v plus u. So this is the formula for pre-relativistic physics, pre-Einstein physics. W is equal to v plus u. It can't be the right thing. We know that in relativity theory it's impossible to exceed the speed of light. And if I can move with 3/4 of the speed of light relative to you, and he can move with 3/4 of the speed of light relative to me, if we use this formula, he is going to be moving relative to you with 1.5 times the speed of light. So something's wrong. This can't be right. To figure it out correctly, all we need to do is to compound two Lorentz transformations, one with velocity v and one with velocity u. And that corresponds to matrix multiplication. Let's just, we don't need y and z in here. Let's write down the matrix for the transformation between you and me. Okay, that's just 1 over, let's see, what is it? It's 1 over square root 1 minus v squared, v over square root 1 minus v squared, v over square root minus v over square root 1 minus v squared 1 over squared 1 minus v squared. I just threw away the everything but the xt part of this transformation. That's the matrix that takes us, let us say, from your coordinates to my coordinates. Now, there's a second transformation which takes from my coordinates to his coordinates. And that transformation has the form, let's call it x double prime and t double prime. That's his coordinates. And that's equal to 1 over 1 minus u squared square root minus u over square root of 1 minus u squared, u over square root of 1 minus u squared, minus sign, and then 1 over square root of 1 minus u squared. That's the transformation times x prime t prime. So this takes us from me to him, and this takes us from you to me. What is the transformation which takes you to him? Right? All we have to do is plug in for x prime here this matrix times xt. And so we see that x double prime, t double prime is equal we have to multiply these two matrices together to find the transformation between you and him. Okay, this is not so hard to do. Let's actually multiply the transformations. Let's do it. Let's spend 5 minutes doing it. Let's see. We have this times this minus this times this. That's going to be 1 plus uv, I think, in the corner over here. 1 plus uv, if I'm not mistaken. Does that look right? 1 times 1 minus plus u times v. Yeah. Right? What about the next corner over here? That's 1 times minus v and minus u. Say it again. I think it's minus v minus u. Is that right? I think it's also minus v minus u down here, and I think it's 1 plus uv over here. Okay. Now, the question is, does this have the form? Well, what form do we want it to have? Let's see. One over 1 minus w squared square root, w over square root of 1 minus w squared, minus w over the square root of 1 minus w squared, 1 over. In other words, does it actually itself have the form of a Lorentz transformation? And if so, what is the w? Okay. The answer is yes, it does have the form of a Lorentz transformation. But I'm not going to work the whole, I'm not going to prove that this whole matrix here has this form. What I'm going to do instead is just show you how to pick off the value of w. The value of w is easy to pick off. You know what it is? It's just the ratio of this to this. The value of w, if this truly has the form of a Lorentz transformation, then it's easy to pick off the value of w. It's just the ratio of the component over here to the component over here with a minus sign, right? Minus the ratio of this to this is just W. So if all I want to do is pick off the velocity of the compound transformation and not bother trying to prove that it actually has this form, which it does, all we have to do is look at the ratio of this component to this component, and that must be W. So we can read it off. W is equal to U plus V divided by 1 plus UV. That's it. That's all we have to do to figure out what the relative velocity between you and him is. Compound the transformation, go back later and prove that this really has this form. But if all we want to do is figure out the velocity of him relative to you, or to you, all we have to do is work out what the ratio of this component to this component is. Minus v minus, or v plus u divided by 1 plus uv. That's the velocity w. Now, we could put some speeds of light into this. The units of u and v are velocity, and the units of w are also supposed to be velocity. So that looks pretty good. The only thing wrong with it is you can't add uv, which has velocity squared, to 1 unless you first divide it by the speed of light squared. So including the speed of light, w is equal to u plus v. That's what Newton would have said. He would have said just u plus v. But Einstein comes in and throws this thing into the denominator here. Okay. Throws this thing into the denominator. If both u and v are positive, imagine u and v are positive. I'm going down the x-axis with positive velocity. He's going down relative to me with positive velocity. Then 1 plus uv is bigger than 1, and w will be less than u plus v. In fact, this formula will never get bigger than the speed of light. In fact, let's see what it does do if, let's take a crazy limit. Let's see. Let's take a crazy limit in which u and v are both very close to the speed of light. Okay? They're very, very close to the speed of light, essentially equal to the speed of light. Then what does w come out to be? Well, the top becomes just twice the speed of light, and the bottom, that's bad, twice the speed of light. But the bottom, u and v, are both equal to the speed of light. So uv over c squared is 1. 1 plus 1 is 2. It hasn't gotten bigger than the speed of light. Okay? Even if you're compounding two velocities, each of which is exceedingly close to the speed of light, so close that I can say it is the speed of light, I add them up, I get something which is no bigger than the speed of light, in fact, which is just the speed of light. It's not hard to prove that this expression never gets bigger than the speed of light as long as u and v are not bigger than the speed of light. As long as u and v are not bigger than the speed of light, the composite here, the composite velocity, cannot be. And that's easy to prove. But it's more or less clear, since I've gone to the absolute limit where u and v are as big as possible, and I still haven't gotten bigger than the speed of light, it's pretty clear that I can't exceed the speed of light by compounding any number of Lorentz transformations. The result will always come out less than the speed of light. So this is an exercise in matrix multiplication, which is the neat tool for this particular kind of operation. All right, I next want to come to the concept of velocity in relativity. Before we even talk about velocity, let's talk about four vectors. It's evident that the coordinates of a point can be thought of as the components of vectors. X, Y, and Z are the components of a displacement vector from the origin, but x, y, z, and t can be thought of as the components of a four-dimensional vector, including time. Whose components are these objects x mu. X mu are the components of a four-vector. A four-vector is one which includes not just three spatial components, but a time component also. We can have more general objects, just as we can have all kinds of vectors in space, velocity vectors, acceleration vectors, electric field vectors, all kinds of vectors, not only x mu itself. We can have a general concept of a vector, v mu. A vector is a thing which transforms under Lorentz transformations and rotations the same way that x mu transforms. It has four components, and if you want to know how its value in any coordinate system, you simply transform it from coordinate system to coordinate system using the same Lorentz transformation that you coordinate transform x with. I won't bother writing that down, but if you write down the Lorentz transformation for x's and simply substitute in the, instead of x's, v's, that is the way four vectors transform. There are other four vectors. Oh, before we talk about how four vectors transform, this is some, let's also talk about the covariant. This is the contravariant form of the vector and consists of four, v1, v2, v3, v4. There is also the covariant form for the vector, which is just a notational device, exactly the same things, v4, except the three space components have minus signs. You simply change the sign of the space component, and that's equal to v1, v2, v3, v naught. Not 4, naught. Not 4, naught. Sometimes I'll write 4 instead of naught. Just as there's a concept of proper distance of a vector x, there's the concept of the proper length of any vector v, and that is just given by v mu is the length of v squared. We can just call it v squared. It's analogous to x mu is equal to tau squared, where tau would be the proper distance from one end to the other end of the vector. Here, it's just a general notation representing a new concept. It's a new concept. You can't ask me why this is the definition. This is the definition of the length of a four vector. What does it mean? It means v naught squared minus v1 squared minus v2 squared minus v3 squared. Exactly like ordinary vectors, except with this extra minus sign, v naught squared minus v1 squared minus v2 squared minus v3 squared is called the proper length of a vector v. And it can be written in this form, with a lower index and an upper index, implicitly summed over. That's a useful, in fact, you can even go a little bit further. You can say, supposing you have two vectors, v and w, then you can invent the product of the two vectors and think of that as analogous to the dot product of two vectors. I don't know what to call it. This is what it's called, w mu, v mu. But you can think of it as being analogous to the dot product of two vectors in ordinary space. W times v, it represents a kind of product of the two vectors, and the important point is that this quantity is invariant. If you change frames of reference, that changes the components of both w and v, but it does not change w mu, v mu. So quantities like that are invariant. They don't change under Lorentz transformations, and they don't they don't depend on what family of coordinate axes you use. Okay, that's the idea of a 4-vector, but let me come to a particular 4-vector. The particular 4-vector is the velocity 4-vector of a particle. Obviously, we want to talk about things like velocity and acceleration. In Newtonian physics, velocity is a vector. But it's a 3-vector, 3 components. It doesn't have a 4th component. In relativity theory, anything that has 3 components will have a 4th component. And velocity is a quantity which has 4 components. What are those 4 components? Well, let's start with the space components of velocity. Here's what I usually mean by velocity. dx dt, that's the x component of velocity. Let's call that vt. And there's dy dt. Sorry, this is vx. This is vy, and likewise for vz. Okay. This is the ordinary concept of velocity, the time rate of change of the position of a particle. But what would be the time component of the velocity? dt dt? That's just 1. That doesn't make sense. We have an object which really doesn't have 4 components. One of the components here is just completely trivial. This can't be what a good relativist would think of as the velocity. So let me explain to you the way relativity theory views the velocity of a particle. I mean, this is a perfectly good definition of velocity. It's just not a thing which transforms nicely under Lorentz transformations. It doesn't have a nice way of transforming when you transform the coordinates. Here's the definition of velocity that turns out to be more useful. You start with your coordinates. We're working with particular coordinates, x and t, and y and z, t, x. Every point of space-time is labeled with a set of coordinates x and t, x, y, z, and t. Right? Now, a particle moves through here, and along the trajectory, along the world line of the particle, it could also be moving in y and z, it could be moving out of the blackboard, but along the trajectory of the particle, the little displacement is called dx mu. dx mu can represent the displacement along the x-axis, the y-axis, but it can also represent the displacement along the time axis. So dx naught represents the displacement along the time axis, dx represents the displacement along the x-axis, and dy and dz similarly represent little displacements. Right? So we have 4 of them. From here to here, there are 4 little differential distances along the world line of the particle. Okay. Now, ordinarily, I would divide these by dt, but dt is the time as seen in a stationary reference frame. Instead, I'm going to divide it by the dt in the frame of reference of the moving particle. So as the moving particle moves along, it has a watch. And it ticks off time. And it asks, how much has my x displacement, how much have I moved in x in a given amount of proper time? How much have I moved in y in a given amount of proper time? How much have I moved in z in a given amount of proper time? Now, proper time is invariant. It doesn't change from coordinate frame to coordinate frame. So if we divide dx mu by d tau, where d tau is the proper time from here to here, that is a 4-vector which will transform the same way as x does. X mu, or little differences in x mu, transform with Lorentz transformations, conventional Lorentz transformations. Dividing by dt doesn't change that, because dt doesn't change under a Lorentz transformation. So dx dt becomes a 4-vector. It's got 4 components, and let's see if we can see what those 4 components are in terms of the old-fashioned velocity. The old-fashioned velocity, Vx, Vy, and dt. Sorry, Vx, Vy, and Vz was Vz, dz, dt. Let's see if we can relate these things to the old-fashioned kind of velocities. Incidentally, this is called u super mu. It's called the proper velocity. By proper here, it means the time that's being used to differentiate with is the proper time. Okay. All right, let's see if we can figure out what it is. Let's take, for example, dx by d tau. That's equal to dx by dt times dt by d tau. Likewise for y, dy by d tau is dy by dt times dt by d tau, and so forth. In fact, we can even write down that dt by d tau, dt by d tau, that's the 4th component of the velocity vector. That's just dt by d tau. So if I knew what dt by d tau was, I would know how to go back and forth between old-fashioned kind of velocity, dx dt, and this new kind of relativistic velocity, u. Okay. Let's figure out what dt by d tau is. It's not very difficult. First of all, let's write that d tau squared is equal to dt squared minus dx squared minus dy squared minus dc squared. That's just the definition of a small proper time interval here. It has a dx, it has a dy, it has a dz, and it has a dt. And the proper length of that little vector is dt squared minus dx squared minus dy squared minus dc squared. Okay. Now, let's divide this by dt squared. Well, this is just 1 minus, now what is this? This is dx dt squared. That's vx squared. This is vy squared. And this is minus vz squared. But what's vx squared plus vy squared plus vc squared? That's just the magnitude of the velocity of the particle. And that's the magnitude of the ordinary velocity. That's the magnitude of the ordinary velocity. And so this is just 1 minus v squared, where this v here represents the full velocity of the particle. That's equal to d tau by dt squared, or better yet, d tau by dt is equal to the square root of 1 minus v squared. That's great, because I now know what dt by d tau is. It's just 1 over this. So dt by d tau is equal to 1 divided by square root of 1 minus v squared. That tells us that, let's write down the equations now. Ux is equal to dx by dt, that's vx, times dt by d tau, that's square root of 1 minus v squared. Likewise with uy and uz, y divided by square root of 1 minus v squared, and uz is equal to vz over square root of 1 minus v squared. What about the 4th component? The 4th component is just dt by d tau. Right? dt by d tau, dx by d tau, dy by d tau, dt by d tau, and finally dt by d tau. That is just u0, which is equal to 1 divided by square root of 1 minus v squared. So here are the 4 components of the velocity, of the relativistic velocity vector in terms of the ordinary velocities. Okay? Notice that if the velocity, this really should be, as always, a c squared down here, v squared over c squared. And notice that if the velocity is small by comparison with the speed of light, then the thing in the denominator is just 1. ux is the same as vx, uy is the same as vy, uz is the same as vz, as long as the velocity is small by the comparison with the speed of light. And u0 is just 1 dt by dt. That's if the velocity is slow. But when the velocity gets fast, there's appreciable differences between u and v. In fact, u is typically, let's see, 1 minus v squared, so this is bigger than 1. U is typically less than v. Is that right? No, u is typically bigger than v. Yeah, u is bigger than v. U is typically bigger than v. I take that. 1 minus v squared, yeah, u is bigger than v. And in particular, u0 is nowhere near 1. It gets huge. Okay? This is the concept of the relativistic four-vector of velocity of a moving particle. It's a four-vector. It transforms. If you know it in one frame of reference, you can compute it in any other frame of reference just by transforming it the same way as x, y, z, and t transform. And that makes it much easier to work with than the ordinary velocity, which has a very complicated transformation property. Now, I'm going to stop soon, but let me just tell you another way of thinking about this four-vector of velocity. It has an analog in ordinary Euclidean geometry. Anybody know what it is? It's the tangent vector to a curve. If you have a world line, then this notion of four velocity is basically, here it is basically the tangent vector to the trajectory along the trajectory. But let me show you about tangent vectors in ordinary geometry, not relativistic geometry. Imagine you have some curve in space. Two-dimensional space, three-dimensional space, it doesn't matter much. And I want to construct the components of the tangent vector. The tangent vector means a vector along the curve of unit length. A unit vector, which is tangent to the curve at this point here. Well, the little differential displacement here, dx, now I'm talking only about ordinary space, is obviously pointing along the tangent vector. It's just this little vector over here, from here to here, dx. It points along the tangent vector, but it's not a unit vector, it's a very small vector. What do we want to do to make a unit vector? And I'll tell you what we want to do. We divide dx by the distance along the curve. In other words, we take this little differential displacement that gives us dx, dy, and dz, and we divide it by the distance along there. What is the distance along there? It's ds squared is equal to dx squared plus dy squared plus dz squared. And we simply define the tangent vector to be dx by ds, dx, dy by ds, and dz by ds. This is for ordinary geometry, no time, just ordinary space. We define the tangent vector. Incidentally, can you see why this tangent vector is a unit vector? It's because the sums of the squares of each component are equal to 1. Why is that? Because ds squared is dx squared plus dy squared plus dz squared. All right? So if I square up the components and add them together, dx squared plus dy squared plus dz squared is ds squared. And so this is a unit vector And it's just gotten by taking the little differential displacement along the curve and dividing it by the small distance along that differential displacement, and then letting it shrink to zero, ordinary calculus. This is the same idea here. Instead of dividing by the ordinary distance, you divide by the proper time between the points. You have a little dx, and you divide by the proper time. So this is the analog. This is the relativistic analog of the tangent vector along the world line of a particle. As I said, its space components, if the particle is moving slow, its space components are the ordinary velocity, and its time coordinate is just 1. If the particle is moving fast, then these are appreciably different than their non-relativistic analogs. Yeah?
If C equals 1, proper time and proper distance are the same.
Say it again?
If C equals 1, proper time and proper distance are the same thing.
Proper time is usually something measured along a time-like trajectory. If C is equal to 1, apart from the funny minus sign that's appeared, yes. You can't, by taking C equal to 1, you can't get rid of a minus sign in a formula. So I'm not sure what you mean by saying is proper time the same as proper distance. Oh, I'm sorry. You mean here I was simply talking about ordinary Euclidean geometry. Distance is distance. There's no question of proper time because time doesn't even come into it. Okay? Proper distance, and I've called that S. Okay? In relativity, the analog along here, along a trajectory, is d tau, and I would call it proper time. Here I would just call it distance. Here I would call it proper time. You could call it proper distance if you like, but it doesn't add very much. It's just a distance measured by a tape measure along the curve. All right. Here it's also just distance, but distance measured by a clock along the curve. Yeah. So it's basically the same concept, the tangent vector, the velocity vector. Now, of course, you can differentiate the velocity vector with respect to proper time along the curve, and that gives you the proper acceleration vector. Why would we be interested in the proper acceleration vector? Because the analog of Newton's equations, F equals ma, becomes a statement about proper acceleration. But proper acceleration is not the second derivative of x with respect to t, but the second derivative of x with respect to distance or with respect to proper time along the curve. So if we want to understand how Newton's equations change, we want to understand proper velocity, proper acceleration. Another example, let's see, I think we could, shall I stop here or should I go another 10 minutes? All right, we'll go another 10 minutes and just illustrate the concept of momentum. Momentum is an important concept in mechanics. We haven't gotten to mechanics yet, but as you might imagine, we will have a relativistic concept of momentum. Momentum is a vector in ordinary physics. In relativistic physics, it's part of a 4-vector. Okay, so let's go through that. In ordinary Newtonian mechanics, mv is equal to the momentum p. We could put some indices on here, the x component of velocity, y component of velocity, or we could just put a little vector index here to tell us that we're talking about vectors. So momentum and velocity are vectors. Mass is just a number. Incidentally, in the modern terminology, one doesn't speak about mass changing with velocity. Mass is simply a characteristic of a particle that it's what used to be called rest mass. When one speaks of mass, it's a number that's attached to the particle. It is what used to be called mass when the particle is at rest, and we'll see what it's connected to. But just think of mass as something associated with a particle and not with its velocity. So if you look up the mass of an electron in a table of masses of particles, it won't tell you the mass as a function of velocity. It will just tell you the mass of an electron is blah, 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 blah kilograms. And it doesn't change with velocity. It's simply the number that's attached to the electron. Okay, the analog of momentum, in fact, the momentum of a particle in relativistic theory is not gotten by multiplying the mass by the ordinary velocity, but rather the mass by the relativistic velocity. So the right definition in relativity theory is that p mu with 4 components is equal to the mass times u mu. That's 4 components. Momentum in non-relativistic physics only had 3 components, but it's interesting to ask what the 4th component is. I'll tell you next time how you use the momentum. You use the momentum because it's conserved. If you want to know what happens to particles when they collide or particles when they decay and so forth, the basic tool is conservation of momentum, but not conservation of 3 components of momentum, but conservation of all 4 components. So we ought to find out what the 4th component of momentum is. What about the first 3 components? Px, let's say. That's m times ux, which is m times vx divided by square root of 1 minus v squared over c squared. Okay. If v is small, 1 minus v squared over c squared is basically just 1. And so for small velocity, the momentum is just mv. All right? As the velocity gets bigger and bigger, the momentum starts changing and deviating away from just mv. In fact, it gets bigger than just mv. But for small velocities, it's just a good old momentum. What about the time component? This is something new. Or is it? What about the time component, or equivalently p0? What is it? All right. It's energy. Energy is also conserved. And the 4th component of the momentum vector is energy. Let's see if we can see why that's true. First of all, it's m divided by the square root of 1 minus v squared. And let's put in the speeds of light now. Now, I lied to you a little bit. I said that pt is energy. It's not quite true. You have to multiply it by the speed of light squared to get energy. The main point is that it's conserved. Whether or not you multiply it by the speed of light squared is a matter of convention and a matter of making it consistent with older choices of units. Energy has certain units. What is the energy? What are the units of energy? The units of energy are mass times velocity squared. Where did I get that from? 1/2 mv squared is the kinetic energy of a particle in ordinary relativistic physics. So if pt has anything to do with energy, then you better multiply it by c squared in order to have it units of energy. But apart from units, it's just pt. Apart from putting in the appropriate powers of c to give it the units that we're familiar with when we talk about energy, pt is the energy. Let's see, let's go a little bit further. Let's work this out and see that it's energy. See that it's related to non-relativistic energy, kinetic energy. All right. First of all, this is mc squared times 1 minus v squared over c squared to the minus 1/2 power. Because it's in the denominator, it's to a negative power, and because it's a square root, it's the power 1/2. Okay. Now, I want to work this out for small velocities, for velocities very much smaller than the speed of light. To do that, we use the binomial theorem. The binomial theorem says, the main thing for our purposes is that what the binomial theorem says is that 1 minus a small number, let's call it epsilon, to any power p is approximately equal to 1 minus p epsilon. That's the binomial theorem. You can, for example, there are higher orders in epsilon, plus things of order epsilon squared, epsilon cubed, whatever, higher orders in epsilon. But for example, 1 minus epsilon squared is 1 minus 2 epsilon plus epsilon squared. Epsilon squared is very, very small. We're not interested in it. What about 1 minus epsilon cubed? That's 1 minus 3 epsilon plus things which are order epsilon squared. If epsilon squared is very small, then 1 minus epsilon to a power is just 1 minus the power, 1 minus p times epsilon. That's what the binomial theorem tells us about general powers of 1 minus epsilon. All right, now, v squared over c squared is small. For a slowly moving particle, v squared over c squared is truly very small for ordinary velocities. And so I can apply this rule, and it says that this is mc squared times 1. Now, we have a minus from here, but we have another minus from here, and it comes out to be plus 1/2 v squared over c squared, plus additional things which are very, very much smaller than v squared over c squared. The next one will be order v4 over c to the 4th. That's impossibly small for any ordinary velocity. And so this is basically a good approximation for slowly moving objects. mc squared times 1 plus 1/2 v squared over c squared. And now the rest is familiar. It's mc squared. That's, you've seen that before. But that's only the energy if the object is at rest. If it's moving, there's another term which is 1/2 m, the c squares cancel, v squared. This is the ordinary Newtonian kinetic energy of a moving particle, and you add that to the constant mc squared. That's what the fourth component of momentum is. Or at least for slowly moving non-relativistic particles, the fourth component of momentum is a constant which is characteristic of the particle, mc squared, plus the ordinary Newtonian kinetic energy. Adding in a constant to the energy of a particle, if the particle is not allowed to change its mass, and in Newtonian physics, particles never change their mass. If a particle cannot change its mass, and you have any number of particles, then all of this adds up to some constant, and an additional constant in the energy doesn't make any difference. So the important term in the energy when particles are moving slowly is this 1/2 mv squared. That's the term in the energy which depends on the velocity. It's what we call kinetic energy. So that's the 4-vector of momentum includes momentum and energy. The conservation of the 4-vector of momentum is the conservation of momentum and energy. They go together. Okay? Even more, when you Lorentz transform from one frame to another, momentum and energy get mixed up with each other because they're components of a 4-vector. So what is energy in one frame becomes a combination of energy and momentum in another frame, but in every frame the momentum is conserved. That's the important thing. Momentum is conserved in every reference frame, which means all 4 components, energy and momentum, of an isolated system are the same before and after a collision. We'll work out some examples and use it next time. And then I want to go on to Newton's equations, the concept of acceleration, but then wave equations. Wave equations because we're going to want to study electricity and magnetism. We're going to study light. We want to study light waves and so forth. And so we'll want to understand how waves fit into relativity and how particle motion fits into relativity. Particle motion, what's the analog of F equals ma? Okay, that'll be next time. Any questions now? We had a long night tonight, didn't we?
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.